Okay, so as promised, right, here we are, the second of our 2 kidney videos. Again, check below in the description, follow those links, watch those videos. They're amazing. Really, really like that channel. Really doing a good job of visualizing some of the things that we're going to talk about in the next couple of slides. So maybe you want to watch those first, come back and we'll hit those topics. Maybe you want to watch them later. As long as you watch them, really, that's the big key here. Okay, so we've been talking about this loop of Henle, right? Where we have our PCT, big long loop that comes down, comes back up, and DCT, and so on and so forth, right? And what we're seeing here with these 3 different sections, we're basically taking a little chunk out of the middle, right? So we're seeing the descending limb fluid coming down this way, coming back up this way, and ascending limb, and the interstitial fluid between them. In these 2 limbs, the descending and ascending limbs, we have different processes that are at work. So in the descending limb, we are fully permeable to water. Okay, so we are gaining sodium, we are gaining chloride, we are losing water in an attempt to become isosmotic with the interstitial fluid. All right. In the ascending limb, the one coming up, we are impermeable to water, mostly, right? And we are actively pumping out sodium. The combination of these different processes gives us what we're going to refer to here as the single effect, which results in different concentrations of stuff in different parts of the loop of Henle. And one thing that might seem kind of immediately strange about this is that the later part, right, the part where we're coming back up and we're about ready to head out of the nephron altogether, here in the ascending limb, if we look, the single effect means that the ascending limb is actually more dilute than the descending limb. And that might not make sense at first, but it's going to make sense in a little bit. So just kind of hold on. But the single effect here, basically the idea is that we're going to dilute the filtrate coming up the ascending limb. All right, now here again, this is where we're really watching that video is going to help, because it's for me anyway, pretty hard to kind of describe what's happening here. But the end result, right, of this whole process is basically changes in concentrations of both the filtrate and the interstitial fluid. And the change in concentration of the interstitial fluid is the ultimate goal here. Okay, that's really what's going to drive concentration of the urine, not the concentration of the filtrate as it passes through here, but the interstitial fluid. So the basic idea here, process we're going to refer to as countercurrent multiplication. The idea here is that as we descend, okay, the fluid inside the descending limb becomes more concentrated. So we go from 300 milliosmoles to 500 milliosmoles to maybe a total maximal difference here, but in most vertebrates, well, mammals anyway, but 700 milliosmoles, whatever. We become more and more concentrated. Okay. But at the same time, right, as we come back up, we're actively pumping salt out, we're making this fluid, the interstitial fluid, saltier all along the way. And as this fluid becomes more and more dilute, okay, the interstitial fluid itself also becomes more dilute because there's simply less salt to pump out. So in the interstitial fluid, you get really, really, really salty. And the longer that loop is, the greater this countercurrent multiplication effect becomes, and the saltier that interstitial fluid becomes. Okay, that's a big deal. The reason that's kind of the end goal here is that there's one more step to this whole process, right? There's one more thing to think about, and that's we're not leaving the kidney as we leave the loop of Henle, right? P, D, we leave the kidney via this collecting duct, right? Same as we saw back in that old amphibian, right? That collecting duct is in fact permeable to water again. And so as fluid flows down thiswardly, right, this direction, down and out, it passes by all of this salty interstitial fluid, right? Higher and higher and higher and higher osmotic pressure. And so water, as it passes down, filtrate passes out through the collecting duct, it loses water the entire way to the interstitial fluid. Okay. Now, this does not return this fluid to the blood yet. There's yet one more piece to this. And this final remaining piece, blood vessel, that runs right next to, right in parallel with this collecting duct. So I'm going to try to change my ink color here a little bit. So if here is our, I hope you can see this, you probably can't see this. Here is our tubule, and our collecting duct. Running next to this is the vasa recta. Runs parallel to it the whole way. Let's back up. And so as we lose water, do one more change of color here. As we lose water from the filtrate, that water pops and is collected by vasa recta the whole way. So in doing this, right, we end up concentrating the urine, have an easy way to return the water back to the blood. Everybody's happy. Simple as that. And then again, that is mostly really what you'll see in those videos by Ruse there. Again, just thinking about how this works in terms of depth of medullary tissue. The longer that is, the longer that loop is, the greater the amount of salt that we can release, the greater the amount of osmotic pressure we can induce in that interstitial fluid, the more water that we can actually end up bringing back in. The way that this is going to work, right, is that as we get through different parts of this tubule, we have different actual processes going on. So in the early part of the PCT, okay, what are we doing here? Here we've got tubular fluid on the left, the fluid here on the right. We are actively pumping glucose back in or back out of the tubular fluid to be resorbed. Glucose comes back out, bringing back in salt, we're bringing back in chloride. We're resorbing all of that stuff. I guess that's really the take-home message here, is that in this proximal convoluted tubule, all of our processes are really based around trying to take everything we just filtered out, dump it back into the blood. In the ascending limb of the loop of Henle, right? So again, this is the water impermeable part, right? We are actively, the big process here, as before, is this one right there. This active movement of sodium out of the tubular fluid and into the interstitial fluid. We are making that interstitial fluid salty. We are doing our damnedest to make that happen. Now, there are other things that are going to go with that, kind of passively along those lines. We're going to bring chloride with us, or potassium with us, and salt, and all those other things that go with that. Really, the big key is the pumping out of salt, removing it from that filtrate, making the filtrate more dilute. We'll fix that later in the descending and the collecting duct, but making that interstitial fluid as salty as possible. Oh, again, I guess to kind of reiterate what we talked about earlier with ADH, right? The way that we're going to change the permeability of any part of this is entirely on the basis of how many aquaporin proteins are present. How permeable are we to water based around how easy are we going to make it for water to get across. Very, very simple message. There's more to it than that, but that's kind of where I'm going to leave it. Now, bird kidneys are slightly different. Birds are the other group of animal that can concentrate their urine. So we have mammals and birds both do it. Crocodiles can't. Dinosaurs probably couldn't. Non-avian dinosaurs probably couldn't. We don't know, right? We know that birds can do it. And bird kidneys are pretty weird. They have a variety of different kinds of nephron. Some of these, like this guy right here, are what we call loopless nephrons. Some of them are mammalian type, right? Ones with loops of Henle that can concentrate urine. They do both. One of the big things that's different here in terms of the kidney really ultimately is where does the product go? Like other reptiles, they don't dump out into a bladder and then a urethra. They dump their kidney waste products, their uric acid, and other associated parts, dump that into the lower GI tract instead, so into the colon rather than into a urinary bladder. The really big difference between a bird kidney and other reptiles is that other reptiles just these kinds. Only birds have these mammalian type looped nephrons. Outside of the realm of vertebrates, things are interesting. If we look at these guys, these things are called decapods. Stations. So your lobsters, your shrimp, things like that. They have one big thing, essentially, it's called a green gland. Because it is really bright. Not quite this shade of green, but it's green. As soon as they call it an antennal gland, usually the green gland more commonly. It's essentially one giant nephron. That's basically what it does. And it does basically the same thing that a nephron does. It produces urine. Simple as that. Mollusks have kidneys that are exposed to the mantle cavity. So they don't have a bladder. They don't dump it into the GI tract. They don't really have a GI tract in the same sense that like a bird does. They just kind of dump it into that big open mantle. And the way in which they produce filtrate is extremely different. Okay. If you remember from before, octopodes here have three hearts. They have a systemic heart, and then they have two branchial hearts prior to both of the gills. These branchial hearts have a little appendage that sticks out into a pericardial sac. And that pericardial sac is connected to this little dude here called a renal sac. And the renal sac also has little appendages here, renal appendages from the major blood vessels that come in here. And filtrate is produced here from these blood vessels and actually from this branchial heart appendage, rather than from a nephron or anything else like that. And so the whole of the kidney is this pericardial cavity, renal pericardial canal, and renal sac together that just produces basic filtrate. That's pretty wild, honestly. It is pretty wild. For clams, other bivalves, other kinds of mollusks, so not like octopodes, a similar situation is happening here, only instead of it being the branchial hearts, it's the systemic heart that's actually responsible for producing the filtrate via this pericardial cavity. For insects, they don't have kidneys at all. They actually have instead little outpocketings of the GI tract, sides here, called Amphibian tubules. The Amphibian tubule and the hindgut both produce urine, but they don't do it by filtration. So they do it instead by secretion. So the cells lining the hindgut, the cells lining the Amphibian tubules secrete urine into the hindgut here, and it's excreted with the rest of the wastes. One final thing, my final slide for you, I guess, for the semester, has to do with transitions for amphibians as they become terrestrial. So if you remember when we talked before about fish, right? About fish constantly, right? And because they constantly urinate, they can leave their nitrogenous as ammonia, right? And they can get away with this because they live in an aquatic environment. They live in a freshwater environment, right? And they are, as a result, constantly being inundated with water. They have more water than they know what to do with, right? Well, the same basic conditions, right, are what's present in tadpoles. They have the same problem, right? And so tadpoles are, because they're spending so much energy trying to grow, right, and to not be eaten, if they can save energy anywhere, they're going to do it. And they're going to save energy by producing ammonia, right? Because they live in fresh water, they can constantly urinate, they don't have to worry about this stuff. But as we transition from water to at least partial landness, right, we can't do that anymore. We have some water budget we have to maintain. We can't just pee wherever we want to, right? And so we see that during metamorphosis, in amphibians that undergo metamorphosis, we see this transition from production of nitrogenous waste as ammonia to that as urea. And that's really the take-home message on that. Okay. All right. So I hope it's been a good semester. I know it ended kind of weird. Certainly weird for me to kind of end it this way, but here we are. I will be posting a study guide soonish, I guess. I don't know when, but there will be one for the final paper, final exam here in the next probably few days. All right. So if you could, please go ahead and do the idea evaluations. I know, again, it is what it is, but it would be helpful to me personally if you could do those for me. So please go ahead and do that. And I'll see some of you next semester. And for those of you who are graduating, good luck. I will see you guys hopefully as you come back and share all of your success stories and do all that wonderful stuff.